Okay, we've looked at tackling the direction of the magnetic field around a straight current-carrying wire. What about its magnitude? The magnitude is given by this formula, B is equal to mu naught I over 2 pi r, where mu naught is called the permeability of free space. You may remember in dealing with electric fields, there is a very important constant, epsilon naught, which is related to the Coulomb's law constant. You guys might remember that K is equal to 1 over 4 pi epsilon naught, and that K is in the Coulomb's law, KQ over R squared. This value epsilon naught deals with electric fields, and the magnetic field version of that is mu naught. Now, epsilon naught is called the permittivity of free space. Mu naught is called the permeability of free space. And it's just a constant. Its value is 4 pi times 10 to the minus 7, and the units are Tesla, which is, of course, magnetic field strength, times meters, then divided by amperes. So this is not area here, this is amperes for current. And so if you plug those units into mu naught up here, you'll find that everything cancels out and leaves you with a magnetic field strength in Tesla, which is the units of B. Now we can note that the strength of the magnetic field around a current-carrying wire, around a straight current-carrying wire, it depends on two things. It depends on how big the current is. So if you have a bigger current going down the wire, you get a bigger magnetic field. And it also depends inversely on the distance r away from the wire. So imagine that I have a current coming out of the page, and remember we would draw that as just a dot, and that current would be coming out of the page. If it were going into the page, we would represent it by an X. But if we apply our right-hand rule, we know that the magnetic field line for this kind of a current is going to be going counterclockwise. And so if I pick a spot and draw a loop counterclockwise, that spot would be at any value r. And that's the r here in this formula. And so if I go to any r value, that means anywhere on this circle, anywhere on the circle is going to have the same magnetic field strength, B. And if I go to a different r, if I make r bigger, the magnetic field strength is going to decrease because you're dividing by a bigger number, but you're going to have another loop at a different radius that is going to be a different value of the magnetic field. So if I go out to some other radius, I could draw another loop, and of course we'll pretend that those are concentric circles, but you guys get the idea. We have these loops represent the magnetic field strength determined by this formula. So the direction is determined by the right-hand rule, and the magnitude is determined by this formula, which tells you the value of the magnetic field strength at any distance r away from a wire carrying a current I. So let's look at a couple of examples applying these formulas that we have. The formula for the force acting on a wire and the formula for the magnetic field around the wire. So first let's do a simple example to calculate a magnetic field. So let's say we have two wires. And so I've got a wire that's going to have a current I coming out of the page. And so we'll call this I1. And then we'll have next to it a wire carrying a different current, I2, that is going into the page. And so this would be a current I2. And let's further say that the distance between these two wires is 1 meter. That's just a nice number for plugging into our formula. It could be any distance, obviously. You just plug in whatever the distance was. But here is our basic setup. And so we have two wires, each carrying a current. And let's say that I1 has a magnitude of 10 amps, and I2 has a magnitude of 5 amps. And again, what we want to do here is we want to find the magnetic field strength at a particular point. So let's say we want to find the magnetic field strength at some point P, which is at a point 8/10 of a meter away from the leftmost wire. And so from here to here is 0.8 meters. And then you have, of course, 0.2 meters to the other wire. And so we have the distances from each wire. We can apply the formula for the magnetic field strength and calculate the magnetic field strength from each of these two wires at point P. Now the thing that we have to remember is that magnetic fields are vectors. So we have to get the magnitudes using our magnitude formula, but we have to also find the directions. Once we have both the magnitudes and the directions of these two magnetic field vectors, we can do vector addition and get the total magnetic field at that point from those two wires. Now let's consider the directions. We can consider the direction of the magnetic field around the current 1. Now current 1 is coming out of the page. And so if we apply our right-hand rule, we know I'll stick our thumb along the direction of the current. That means our thumb is going to stick out of the page. And if you wrap your fingers around and make a fist, your fingers are going to curl in the counterclockwise direction. So that means the magnetic field is going to be looping around the wire in a counterclockwise fashion. And so at the point P, it's going to be looping up, and the magnetic field is going to be tangent to that circle there. So we can actually draw in the magnetic field from the first wire, and that's going to be B1. And of course this point is on the line joining the wires, and this is going to be tangent to that looping magnetic field. So that's going to be the direction of B1 is going to be straight up. Now if we similarly look at the magnetic field from I2, we know that I2, the current I2, is going into the page, and so we would take our right hand and we would make our karate chop shape, and we would point our thumb along the direction of the current. We would point our thumb into the page, and then we would curl our fingers wrapping around, as if wrapping around the wire, and we would see that our fingers would curl clockwise. And so that's going to create a magnetic field also pointing upwards. And so we were going to have another vector B2, and it's going to be tangent to the circle around this wire in the same way, but you'll see that both B1 and B2 are pointing upwards. They're pointing in the same direction, and so doing the vector addition is going to be pretty straightforward. You just simply add the two vectors together. Now it's just a matter of applying the formula, plugging all the values into the formula to get the magnitudes. So for B1, we get that that's going to be equal to mu naught I over 2 pi r, and that's equal to 4 pi times 10 to the minus 7 Tesla times meters divided by amperes, Tesla meters divided by amps, times the current, which for the left wire I1 is equal to 10 amps, divided by 2 pi times the distance between them, which is going to be 0.8 meters. Again, we'll have that be 2 pi times 0.8 meters. And that gives us the formula that we need. Now, we can do some cancellations here pretty easily. We can see that the 4 pi here is going to cancel with the 2 pi and leave us with just 2 up top. And here we have 10 to the minus 7 times 10, so that's going to cancel that out and make that 10 to the minus 6. And so we have 2 divided by 0.8 times 10 to the minus 6. And that gives us 2.5 times 10 to the minus 6 Tesla. And similarly for B2, we plug in the value of 5 amps and 0.2 meters. And so that's going to be 4 pi times 10 to the minus 7 Tesla meters per ampere times 5 amps divided by 2 pi times 0.2 meters, and that works out to be 5.0 times 10 to the minus 6 Tesla. And so we can add all of these together, and we get that the total magnetic field is just 5 plus 2.5 times 10 to the minus 6, or 7.5 times 10 to the minus 6 Tesla, and that would be the magnetic field from both of those wires at our point P. Now let's look at our same two wires. We can consider a wire with I1 coming out of the page and I2 going into the page with the same values that we had before, 10 amps and 5 amps respectively. The two wires are separated by 1 meter. And the question that we want to ask is, what is the force between these two wires? We know that each of these wires is going to generate magnetic fields around it. And we know that magnetic fields create attractive or repulsive forces. And so these wires are either going to attract one another or they're going to repel one another. And so what we want to do is we want to find out the force between these two wires and also the direction, whether they're attracting or whether they're repelling. Now, one of the things that's interesting is that it turns out that the amount of force depends on how long the wire is. If the current's going over a longer path between these two wires, you're going to get more force. So actually what's usually determined most of the time when you're working a problem like this is not the force, but the force per unit length of the wire. And so for every meter of wire, how much force do you get? That's the question that we're asking. So the force per length between these two wires. So the way to do this is to think about this in multiple parts. Now we're going to end up with a formula for the force between two wires, but I really strongly recommend against just trying to memorize that formula, because honestly it's something that you'll use so rarely you'll never remember it. But if you think about how to apply the basic formulas that we already know, you don't have to just memorize another formula. You can derive what it has to be based on a couple of simpler formulas that you do already know. Okay, so let's look at the question of determining the direction. In other words, what's the direction of the force between these two wires? And I'm going to pick, to start with, I2. I want to figure out what is the direction of the force acting on the current I2. So, how do I get that? Well, it's a two-step process. The first step is to figure out what's the magnitude and the direction of the magnetic field at I2 from I1. In other words, I1 is creating these circular magnetic loops around it. And so when you get over here, there's going to be a magnetic field right where I2 is caused by the current I1. And we want to know what's the magnetic field vector at the second wire. And so we do the same thing we did in the last example. We first look and we notice that the current is coming out of the page. And so if we do our right-hand rule, we loop our fingers, make a fist with our thumb pointing straight out of the page, we're going to see that our fingers curl counterclockwise. And so there are going to be loops around the wire going in the counterclockwise direction. And when you get right here, that counterclockwise loop is going to be going up. So the direction of the magnetic field from wire 1 is going to be pointing straight up. And I'm going to call that B1 because that's the magnetic field from the current I1. And we know that the magnitude of B1 is just given by that formula, mu naught I, and in this case it's going to be I1, that's very important to keep those subscripts right, over 2 pi. Now, it's generally over 2 pi r, but we're talking really about the distance between the wires, so I'm just going to say, I'm going to call that d for the distance between the two wires. But this is our same formula, mu naught I over 2 pi r, for the strength of a magnetic field around a current carrying wire. Now the next thing that we want to look at is the force acting on current 2. And we know that the formula for the force on a wire passing through a magnetic field is just going to be ILB sine of theta. Now the I in this case is I2, and then we're going to have the length of the wire, and then it's going to be B, but the B that we're talking about is B1, and then we're going to have the sine of the angle between them. But look at the current. The current's going into the page, the B vector is going straight up. Those are at a 90-degree angle, and so we know that that's going to be 90 degrees in this case, and the sine of 90 degrees is just 1. So the force, and this is the force on wire 2, is going to be I2 times L times B1. It's that simple. And so now to simplify this, we can take this value of B1 and plug it in. So if we do that, we get for the value of F2, that's going to be equal to I2 times L times B1, which we're going to plug in as mu naught I1 over 2 pi d. And then we're going to say that is all three of these values, and that is the value that we would plug in. Now, typically, remember we said we wanted the force per unit length, so I'm going to divide both sides by the length, and I get F2 over L is equal to, and I'm just going to rearrange this a little bit to make it pretty, mu naught I1 I2 divided by 2 pi d, where those are the I's are the two different currents. Mu naught is that constant, the permeability of free space, and d is the distance between the wires. And so if we plug all that in, we get 4 pi times 10 to the minus 7 Tesla times meters per ampere times the two currents. That's going to be 10 amps times 5 amps. All divided by 2 pi times the distance between them, which is 1 meter. And we can, of course, do a little bit of canceling. And, of course, that becomes 50 amps squared there, divided by amps. It all works out when you do the units, and you end up with the force per unit length is equal to 1 times 10 to the minus 5 newtons over meters. And that is the force on the rightmost wire. Now, what about its direction? Well, the direction is going to be pretty straightforward because we can see that we have a current going into the page, and so we can apply our other right-hand rule. We make our fingers into that karate chop shape with our thumb extended at a right angle, and we point our fingers into the page. We point our fingers along the direction of the current, and then we rotate our wrist so that when we curl our fingers, they point towards the B, so they'll be pointing towards the top of the page. And if I do that, the direction of the force turns out to be to the right. And so that's going to give me the direction of that force being to the right. And so now we know what the magnitude of the force is and the direction of the force. We can see that it's going to be repulsive. It's going to be pushing the wire away from the other wire, and it's going to have a value of 1 times 10 to the minus 5 newtons for every meter's length of wire. Now, what about the leftmost wire? We could do the same thing. We could say, okay, the magnetic field from this wire is going to be pointing upwards on the left. So if I stick my thumb into the page and apply my right-hand rule, I'll see that the magnetic field for that wire is clockwise, which means that over on this side it's going up. So there would be a magnetic field pointing upwards at this wire, and we could calculate its strength, we could calculate its direction and do the same thing, but there's a shortcut. We don't actually have to apply this twice. Once we get the force on one wire, we can simply say Newton's third law. For every force, there's an equal and opposite reaction force. So if I1 is pushing on I2 with this force in that direction, I2 must push on I1 with an equal and opposite force. Now, I would encourage you as practice to make sure that you try this. Do all this stuff that we just did here. We started with this wire. We calculated the force on that wire using this approach. I recommend strongly that you do the same thing, but start with this wire and calculate with the force on that wire. And what you should see is that it has the same magnitude, but a direction pointing to the left rather than to the right. Equal and opposite forces. So give that a shot. If you have any questions about that, just let me know and I'll try to help you out. Okay, so very often the angles involved in these types of problems is 90 degrees. And we get that sine of 90 equals to 1, so it just kind of disappears. I just wanted to work a pretty simple problem real quickly to show you what happens when that angle's not 90 degrees. And it's pretty straightforward, but let's say that I have a current that is going to the right, and I have a magnetic field that is pointing at a 60-degree angle to that. So this would be the magnetic field, and this magnetic field is making a 60-degree angle with the current. What would be the force on that wire? Well, we simply apply our formula. F is equal to ILB times the sine of 60 degrees, and you can see that you would plug in the values for the current, the length, and the magnetic field strength, the sine of 60, and you'd calculate the magnitude of the force straight away. Now, what would the direction of the force be? The force direction, if I line again, I make my fingers into that karate chop shape with my right hand, I point my fingers into the direction of the current, and then I rotate them. I'm going to be rotating them 60 degrees so that they line up with the B. And if I do that, my thumb is pointing upwards, or rather I should say, my thumb is pointing out of the page. And so the force would have a direction out of the page. How do we notate that? It's the little dot. If the force were going into the page, we'd make a little X. It's that simple. Now, one other thing that we can note, what if the magnetic field is in the same direction as the current? So I've got a magnetic field going to the right, and I have a current also going to the right. What's the direction of the force on that? Well, the angle between them is 0, so instead of sine of 60, we'd have the sine of 0, which of course is just 0. So there is no force if the current is parallel to the magnetic field. No force. Because theta equals to 0. Now, going back to the previous example of calculating the force between two current-carrying wires, we can, I put this slide in, we've already covered this. We get that the magnitude of the magnetic field strength would be that would be the magnetic field strength at the second wire due to the current in the first wire, and then we can plug that in here, and we get that the force looks like that for the force on the second wire. And we can also divide by L to get the force per unit length if that is what we want. Now, if I go on to the next slide, you'll see that if the currents are going in opposite directions, that's basically the example that we looked at, the force is going to be repelling. It's going to repel the two wires. But if the currents are going in the same direction, here they're both going upwards, the force is actually going to be attractive. You could try to memorize this, but really you would forget it a day after the test. But if you understand the approach of how to use the right-hand rules to figure out what's the direction of the magnetic field, remember, what we did when we did the examples, we looked at them as if they were coming out towards us. So on the left, that configuration would look something like this. Two currents coming out of the page, or possibly two currents going into the page, two currents in the same direction. And in both of those situations, that's going to give you the direction of the force on those two wires as being attractive. Now, the other situation that we have over here is current in opposite directions. So we could have that configuration where one current's going out of the page and one's pointing into the page, or we could reverse that and have it be in the opposite sense. But the key thing here is that the currents are going in opposite directions, then the force is going to be repulsive. And that's how to see the current, the effect of the current going through two wires in terms of the force applied on those two wires from the magnetic fields. Now, here are four different examples, these four configurations that I've just drawn over here and over here. Play with this. Can you figure out what direction the force would be on a particular wire starting from the other wire? If you can do that, then you've got these right-hand rules down pretty solidly. And that's how you calculate the magnitude and the direction for the force between two straight current-carrying wires.